I'm gonna continue the discussion about stereoisomers. So in this video we're gonna talk about diastereomers. This is gonna be a relatively fast video just because there isn't a lot to it. From the previous video I talked about enantiomers, which are basically compounds that differ at every single chiral carbon that they have, but diastereomers are a little different. So what diastereomers are is that they still have chiral centers, so you'll still be responsible for figuring out what a chiral center, like how many chiral centers a compound has, and in terms of figuring out how many stereoisomers there are. But when you're looking for diastereomers, what you're going to be doing is you're going to be looking for a compound that just differs at one or two of the chiral centers, but not all of them. And then at that particular location, you're also going to invert the configuration. So I'm going to give you an example of it. I kind of drew out the backbone for glucose, so I'm going to go ahead and fill it in. So you're going to have a CH2OH down here. You're going to have a CHO up here for both of them. If I were to draw a mirror down the center, so you're going to have your OH groups right like that. So when I'm drawing the diastereomer for this one, what would happen is I would have one of these OH groups on the opposite side, or two or three of these groups on the OH on the opposite side, but not all of them. So it would end up being something like maybe this. If this is what I had and everything else is the same, it would be considered a diastereomer. I could still keep this one over here and keep everything else the same. It would still be a diastereomer. I could just do this and it would still be a diastereomer. And I could also just go ahead and add the last OH and do that, and it would also be a diastereomer. But if I were to change this OH group into something like this, then you would be making that an enantiomer because you're differing at every single chiral center in the molecule. So this would not be an enantiomer. Instead, if this is my case, this would be a diastereomer. And kind of going back, I could still have these two on this side, these OH groups on the right side, and it would still be considered a diastereomer. The main takeaway is that as long as all of the chiral centers are not reversed, then you're good. There are chances that it might be a diastereomer. Another thing that I was talking about is basically the inversion of configuration. So what I do here is, let's say I have a carbon, okay, and then I have 4 bonds attached to it. Let's say I have a carboxylate group, a hydrogen, a CH3, and a, what should I put down here? Let's just say an OH group, okay? So when I talk about configuration, I'm talking about R and S classification. So what you're going to do is you're going to be assigning priority to all of these and kind of figuring out which way it'll go. If it goes in the clockwise direction, it is R. If it goes in the counterclockwise direction, it is S. The way I do it is the right way around the clock is R, and then the way going around is the stupid way to go around the clock, so S. So that's how I remember which one's R and which one's S. So from there, what happens is you're going to go ahead and look at your top priority groups. I usually do that by looking at the atomic number of each group. So hydrogen, you know that is whichever one weighs more. So atomic weight. So off these, you already know that hydrogen is going to weigh much less than any of these other groups. So what you're going to do is you're going to go ahead and put a 4 over there, meaning that it's your it's not in your highest priority. It's your least priority group. And then you look at each of the other atoms that you're attached, the carbon is attached to. So what you would do is you would look at the oxygen and carbon. Oxygen has a higher atomic weight, so that's going to be of higher priority when compared to both of these. And now when you look at it, you see that you have carbon attached to a carbon and a carbon attached to a carbon. Under those circumstances, what you do is you go ahead and you look at the next atom. So in this case it's an O, in this case it's an H. So since oxygen has higher weight than hydrogen, this is going to be your second priority group, this is going to be your third priority group. And when you kind of draw an imaginary circle, you kind of see that it's kind of like going in the right direction. This is going to be your R configuration. So this is probably one way you'll see it. So this will be your R configuration. So when you do the exact same thing for glucose over here, if you have a diastereomer, let's say that this was initially R. If you have a diastereomer, the configuration at that particular chiral center will reverse as well. So an R over here will become an S over here. So this configuration will be different at every single chiral location except one. If you're talking about enantiomers, you're going to see a different configuration at every single chiral center. To go in a little bit more detail about the RNS classification, I'm going to do a few more examples with the exact same groups that I used here, just to keep it simple. So just try to follow along with that, and hopefully that'll give you a better idea of how to do RNS classification and determine diastereomers. So other ways you can see it is you'll already have something like this. So, and then I randomly just put groups on here. You're probably going to see a lot of different configurations similar to this. This is called the wedge and dash configuration kind of thing. So what you're going to do is you're going to do the exact same thing. You're going to be labeling your priorities first. So from the previous little example, we already know that this is going to be 1, this is going to be 2, this is going to be 3, and this is going to be 4. So your goal usually is to have your highest priority group to be on the wedge position, but sometimes you'll already have a problem where that's not the case. So what you do is you just go ahead and label it as you normally would if it was just a regular stick figure without any wedges or dashes. And then if your lowest priority group is on the wedge position, you would just have to inverse your overall chemistry that you get at the end. So you would see that right now in this order you're going in the S direction, but since your lowest priority group is on the wedge, you would have to flip that, and that would now become R, and then this would be the R configuration for this particular compound. So there are other ways that people do it. Some people just rotate it until you get to the appropriate, wedge and dash position. But I find that really confusing, so I just keep it simple and I do it this way. So once again, just ignore the dashes and wedges. Just go ahead and label your priorities based off of, like, the atomic weights. If something is like this, if you have a double bond, each bond counts as one link, so you would consider COO instead of just combining the O's together. So they would have a higher priority over a group that just has a CO.